Okay, and the last part of this booklet is key features of graphs. So you've seen all these, but the interesting bit is we're going to try and do this with the year 12s before they know anything about differentiation. So let me know what you think, and if you think this would have helped you to do this before differentiation. So first of all, we have what's called intersection of the y-axis, which we call the y-intercept. So that means we're solving y equals f of x and x equal y-axis, remember it's called x equals 0. So we're solving them simultaneously. So we solve in x equals 0, so we get y equals f of 0. If we want the intersection with the x-axis, or we call that roots, then again we're solving the equation y equals f of x and y equals 0. So we sub in y is 0 and we solve f of x equals 0. So here's a graph. We want to write down the y-intercept and the roots. Well, the y-intercept here is y equals -2. What's the coordinates? That's 0, -2. And the roots, or where it crosses the x-axis, so here and here, so -1 and 2. So x equals -1, x equals 2, which again we can write as coordinates as -1, 0, 2, 0. The next thing which you can remember, an asymptote is the line which the graph approaches as it goes off to infinity. So here's a graph. Let's see if you can spot where the asymptotes would be. Well, you can see hopefully one here. And we normally draw asymptotes as dashed lines because it doesn't reach it when it goes off to infinity. It gets closer and closer and closer. It just never quite touches it. So the distance between the graph and that line gets even smaller. It gets very close to it. So that's one line. So that would be, well, it's y equals 2. And then if you look here as well, there's a line here which the graph's getting closer and closer to, which is x equals 4. So there's my two asymptotes. The next thing, now this is the bit that the year 12s are going to do, like I said, as the second topic before any differentiation. So a point on the curve, so at the point of the curve, we can draw two important straight lines. We can draw a tangent, which is a line that just touches the curve at the point, and a normal, that's a line that's perpendicular to the tangent at a point. So here's the graph, y equals f of x. We're going to draw the tangent and normal lines at x equals 1. So x equals 1, that's that point there. So the tangent just touches it. So that's the tangent. And the normal will be perpendicular. So hopefully that looks about 90 degrees, isn't it? So that's the normal when x equals 1. So what we want to do is we want to use these to help us. So we can talk about the gradient of a line, that's obvious, because for a line, the gradient's the same everywhere. But for a curve, as you can see, look, some bits are steeper than others. So down here, it's not very steep, the graph. Whereas up here, the graph's very steep. So we can't really give the gradient of this curve a number because it's going to change, it's going to vary. So we can say the gradient at a point is the gradient of a tangent. So the gradient at x equals 1, we will just say that's the gradient of that tangent, because each point is only called one tangent. So the gradient at 2, so up here, I would draw a tangent line, and the gradient of that tangent line would be the gradient when x equals 2. So we can make a function of that, so with the gradient function of a curve, and we can use the notation f dash x, that tells the gradient at each point on the curve. So f of x tells us the output to the y value, f dash of x tells us the gradient at a point. So remember, the gradient at a point means the gradient of the tangent. So below here's a curve, y equals f of x, and I've drawn for you 3 tangent lines at -1, at 0, and at 1. So here, and I've given you the equations. and I want you to use the sketch to hopefully write these down. So let's do this column first. Actually, no, let's do horizontally. So when x is -1, so that's here. So this is the point here. So the output is 1. So f of -1 is 1. And f dash to -1 is the gradient. Well, what's the gradient of this line? Y equals 1. It's 0. There's no x's, 0 x's. mx plus c, m is 0. F of 0, so c put 0 in as an input, the output's there. So the output's 2. And here's my tangent line. And here's the equation, y equals 2x plus 2. So the gradient of that is 2. F of 1, so the input is 1. So if I go up here, there we go, the output is 5. And if I want the gradient, f dash, remember, means gradient of 1, I need the tangent line, whichever it is. There's the equation, y equals 4x plus 1. And the gradient, well, the gradient of that line is 4. So f of a number gives me the output, f dash of a number gives me the gradient of that point. Okay, now we know about gradients, we can talk about specific parts of curves. So we can talk about increasing, decreasing, and stationary. So increasing are parts of the graph where the function is increasing. So the outputs are getting bigger. Now, if the outputs are getting bigger, that means the gradient is positive. So because the graph's going up, so the gradient must be positive. So remember, that's the gradient function, f dash of x, must be bigger than 0, must be positive. Decreasing is the opposite, so the gradient must be less than 0. And stationaries are just points on the graph where the gradient is 0. So the gradient function is 0. See, I now use the word derivative. We don't want to use the word derivative of the A12s until we go on to differentiation. We want them to see that differentiation helps us get gradients, but we want them to appreciate gradients before we talk about differentiation. Anyway, so here's a curve y equals f of x. Highlight the parts where the function is increasing in one colour. Well, let's see how many colours I've actually got. So let's do blue for this first bit. Well, it's increasing up until there, and it's also increasing to there. Highlight the parts where it's decreasing in a different colour. I've also got green. So decreasing, what's going down from this point to this point, and put a cross at the stationary points. Well, gradient tangent line would be flat there, and the gradient there would be 0, so it's flat there. So there's my 2 stationary points. So hopefully you notice, look, stationary points split up, increasing and decreasing part of curves. Or they can split up rather. Now, next thing is minimum and maximum. So again, I'm not using f dash or f dash dash. I'm just saying that a minimum are points in the curve where it changes from decreasing to increasing. So minimum goes from decreasing to increasing. So in other words, the gradient of the gradient is increasing. Next, the maximum is where it goes from increasing to decreasing. So that means the gradient of the gradient is going down, it's decreasing. So look, increasing to decreasing, so there's a maximum there. Now we call these points local maximum and local minimum because they're the maximum and minimum in a small region nearby. So that's a maximum from around there, that's a maximum for around, minimum from around there. However, they're not the maximum and minimum for the whole function. So look, there's a point over here that's bigger than there. There's a point over here which is smaller than there. If a graph does have a maximum for everywhere, we call that the global maximum or global minimum. So if I had this curve, for example, then this point there would be the global minimum. Okay, so we know about f dash of x, that's the gradient function. Using the same idea, we can call f dash dash x the gradient function of f dash of x, and we can keep repeating that process. So f dash 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 will be the gradient of f dash dash. So with that in mind, we can have three new things. We have something called convex. So that's parts of the graph where the gradient is increasing, and that means the gradient of the gradient must be positive. The gradient is increasing, so the gradient must be positive. Concave is where the gradient is decreasing, so the gradient of the gradient is negative. The f dash dash of x is less than 0, and we have points of inflection, and that's just where it changes from convex and concave. So here's some examples here. So convex, look, gradient increasing. So all these, the gradients are increasing. Look, the gradient's negative here, it's getting bigger, it turns to 0 here, it's getting bigger, so the gradient's always increasing. So convex looks like this kind of shape, like a U shape. Look, it's always increasing. The gradient starts off negative and gets less negative. Here, concave, this is when it's decreasing. So here it starts off positive, the gradient, and turns into negative. Here it starts off positive, turns into negative. Here it starts off as a small negative number, so like minus 0.1, and here it turns into a very steep negative number, so minus 7 or something. So convex kind of looks like a U, or part of a U, so either this bit of the U or this bit of U, and concave looks like an N. So it doesn't have to be the whole N, look, it can be one side of it. So from here to here, look, this bit would be convex, and from here to here, this bit would be concave, and this point in the middle would be our point of inflection. So we need two different colours again. So we're going to highlight bits of the curve where it's convex and bits where it's concave. So I'll do blue as convex. So it looks like a U from about here to here. It also looks like a U from about here all the way up here. Concave, well, that's here, look, because concave means it's decreasing. The gradient's decreasing, and here, that bit's concave. And the bits where they change are the points of inflection. So the point of inflection about there, point of inflection there, and there. So 3 points of inflection. Okay, so this bit I want you to have a go at this bit yourself. So press pause, try it yourself, and then unpause to check the answers. So describe each section of the curve, use one or more of the words increasing, decreasing, convex, concave. So A to B, well, it's decreasing, and it's also convex. C to E, well, it's increasing and decreasing, so it's account for both of them, and that bit there is concave. F to G, it's increasing, and it's convex because the gradient is increasing as well, look. Here, B to D, well, it's always increasing, but this bit here, look, it's convex, and this bit here is concave. C to D, well, that's increasing still, and it's concave. And D to E, it's increasing, and it's convex. So mark these points on each curve. A, which is a local maximum, B, which is a stationary point of inflection, and C, which is a non-stationary point of inflection. So remember, stationary means the gradient is 0, the point of inflection means it changes. So maximum, well, this point here is the maximum, and point of inflection, well, there's one about here, and there's one here, And this one, the gradient look is stationary. It's 0, gradient 0, and this one, it's not stationary. That must be the non-stationary one here. Maximum, well, that's a maximum point there. Let's look for the stationary point. Well, that looks like there's one there. It looks like there's one there. And it looks like there's one, maybe it's there. So this stationary point, this point of inflection, sorry, is stationary. So that can be B. And these two on looks the gradient's not 0. So either of these could be C. Okay. So I've got a curve here, and this one's a bit more challenging. So mark one or more points in the curve that satisfy this. So f dash x is 0, so that means the gradient 0, and f dash dash x is bigger than 0, so that means it's the gradient of the gradient is increasing, so it's convex. So let's look for stationary. So that's stationary, that's stationary, that's stationary, and that's stationary. So which one is convex? That's concave. That's neither, that's changing. That's convex. There we go. So that can be A. Let's do the other ones where it's f dash to 0. So here, I want the second derivative, f dash dash x to be 0. So that's when it changes. So there. And D, so I want it to be stationary, and f dash dash x is less than 0, so that means it's concave. So it could be here or here, so D and D. Okay, so I've done those. Here I want f dash x to be less than 0 and f dash dash x to equal 0. So I want the gradient to be negative, and I want the gradient of the gradient to be 0. So that means that the gradient, I want it to, the gradient of the gradient to not increase and not decrease. So a good place to look for points of inflection. So the point of inflection there, the point of inflection there, C I've already got. There'll be point of inflection there, point of inflection there, point of inflection there. So 1, 2, 3, 4, 5. So on those points of inflections, where is the gradient negative? So a gradient's positive there, but it's negative there, so that could be B, that could be B, that's positive, and that could be. Whereas this is asking the same thing, but it's saying that the gradient's positive. So that could be E, and that could be E. So that was a bit more tricky. And the following statements are not always true. Sketch a diagram to show how they could be false. If the gradient at a point is positive, then the function must be positive. So I need to try and draw a function where the gradient is positive, but the point itself is negative. Well, if I draw a quadratic, this point here, the gradient is positive, but the point itself is negative. Look, it's under the x-axis. That would be for number 1. If the function is negative, then the gradient must be negative. Well, if I look here, this function here is, actually let's draw a function that's always negative. Let's draw this. If the function is negative, that function is negative, the gradient must be negative. Well, this gradient here, well, all this gradient is positive. So again, that's an example. If the gradient is 0, then the function is a local maximum or minimum. So I need to draw somewhere where the gradient is 0 and it's not a maximum or minimum. So the easiest one is to think of a cubic. That point there, that's gradient 0, but it's not a maximum, it's not a minimum. In fact, it's a point of inflection. 4, if the gradient is always positive, then the function must always be positive. So let's draw a function where the gradient is always positive. So that means it's always increasing. So there's a function where it's always, where the gradient is always positive. However, if I move that function down, like that, then it's negative. So it's not always positive. And finally, if the graph is convex, then the function will always have a local minimum. So if convex like the U, well, in fact, this one will do the job. This is convex, so it's 4 and 5. This is convex. However, this curve here doesn't have a minimum. Look, it's gonna, in fact, it'll have an asymptote. So it will not have a minimum. Okay, and this bit is, I think, the only new bit for you. So here's 4 pairs of graphs, and the graphs of functions, and the inverses. Now let's see if you can spot a relationship between them. So 2x and a half x, x plus 2, x minus 2, x cubed, cube root of x. So you know what x cubed looks like. It's hard when this isn't colour. The cube root of x is this one. Maybe just type in your calculator. And x plus 3 over 2, 2x minus 3. So can you find geometrical relationship between them? Hopefully you can. They're just reflections of each other. So there's reflection in the line y equals x. So I draw the line y equals x for all of them. You should be able to see that's just a reflection. Okay, so use that relationship to draw the inverse of f of x equals 2 to the power x. So there's the graph 2 to the power x. So if I draw line y equals x and reflect it, I get something like that. And in fact, you know, because you've done logs, you know that the inverse of 2 to the power x is log 2x, and that's the graph of log 2x. Using the example above, what do you know about domains, ranges, and asymptotes of the two functions? Well, for the first one, the original, the domain, range, asymptote, method, mowing, the domain is any real number for x. The range is f of x is bigger than 0, and the asymptote is f of x, actually let's use y instead, is y equals x. And for the inverse, the domain, well, it's anything, x is anything bigger than 0. The range could be anything, the output could be anything. So f inverse x is any real number, and the asymptote's this line here, so it's x equals 0. So hopefully what you should spot is the domain, ranges, and asymptotes just switch. So switch between. So the domain of this function becomes the range of this function, of the inverse. The range of the function becomes the domain of the inverse. And the asymptote, I just switch the x and the y. And that's kind of what you would expect if the reflection line is y equal x, and x and y is just switch. So below are the graphs y equals x squared and y equals root x. So why do you think these don't follow the rules? Well, if I try to reflect this here, let's see what will happen. I'll get that big one there, which looks a bit like that, and that big one underneath. So if I reflected that in a line y equals x, I would get this, and this is not a function, because reflecting it, reflection is not a function. So to fix it, what we do, I'll put that in the next page note. No, so to fix it, what we do is we do something called, we restrict the domain. So we say, right, at the minute, it hasn't gone inverse, so x squared hasn't gone inverse, because it's many to 1. So if I restrict the domain, so if I cross some of this graph out, then I can make it 1-to-1. So I cross this side out, because this side's just repeated. I just get this side. So this side now can be reflected to give this bit cross out now, give this. So it can now have an inverse. So if a function is many to one, sometimes I can restrict the domain by crossing some of it out to get an inverse. And we can do that with trig graphs. The trig graphs are perfect examples of many to one functions. Okay, and last bit, last bit of the new bit. If we look back at the graphs of x cubed and the cube root of x, what do you notice about the intersections of the graph? So here, here, and here, what do you notice? And in fact, what do you notice about this intersection here and this intersection here? All the intersections actually lie on the reflection line. The intersections lie on y equals x. So they intersect. So f of x, y equals f of x, y equals f inverse of x, and y equals x, or where they all intersect. So if I'm trying to solve an equation like this, a function equals its inverse, then there's three options. I can either find where these two intersect and solve that, or I can find where these two intersect and solve f of x equals x, or I can solve where these two intersect, so f inverse of x equals x. So we're going to try all three methods to show that all three work, and hopefully you're going to agree that 2 is always the quickest. So let's do the first one. So when the function and its inverse intersect, so x cubed equals cube root of x. Well, cube both sides and times the power, so x9 equals x. Take away x from both sides. I can factorize out an x. Now this bit here is actually difference 2 squares. So I get x, x4 minus 1, x4 plus 1 equals 0. Okay, now if I try to solve that, I get x equals 0. I get x4 minus 1 equals 0, and I get x4 plus 1 equals 0. Well, this has no solutions, because I can't take away 1 and then 4 root it, because x power 4 is always positive. So I put one answer. And on this one, again, I can difference 2 squares it. So I get x squared minus 1 equals 0, or x squared plus 1 equals 0. And for the same logic as this one has no answers. X squared plus 1 can't equal 0. So x squared minus 1, again, difference 2 squares. X minus 1, x plus 1 is 0. So x equals 1, and x equals minus 1. So 3 answers, 0, 1, minus 1. If I try method 2, I get f of x equals x. So x cubed equals x. Take away x from both sides, gives me that. Factorize out an x, gives me that. Difference 2 squares gives me that. So I get x equals 0, x equals 1, or x equals minus 1. So a lot quicker. Then for 3, the inverse equals x. So cube root of x equals x. Well, cube both sides, so I get x equals x cubed, and it becomes the same as that. So 2 and 3 were quicker ones. 1 was the longest one. So if you're ever asked to solve when a function equals its inverse, just make one of them equal to x and solve it. Right, now the rest of it is just transformations, which we've already revised, so I'm not going to make a video on that. And plus, it's just the same as the book you've done this year. So if you want to go through it and try it yourself to revise, you can do, but I'm not going to make a video on it. So any issues, drop me a message.